Afternoon, sir. My name is Nadi Kijera Promise. My course title is 312. The topic I'll be discussing on the type of non-Newtonian fluids and their flow behavior. First of all, starting with the definition of non-Newtonian fluid. Non-Newtonian fluids are substances that do not flow. Non-Newtonian fluids are substances that do not flow. Newtonian law of viscosity, where viscosity remains constant regardless of the applied shear rate. Unlike Newtonian fluids, example water, air, the viscosity of non-Newtonian fluids changes with the rate of shear or stress applied. This behavior results in complex flow characteristics, making these flows distinctive in their response to external forces. Examples include ketchup, which flow more easily under increased shear, and cornstarch slurry, which thickens under rapid stress. Then overview of fluid mechanics. Newtonian versus non-Newtonian fluids. Mechanics distinguishes between Newtonian and non-Newtonian fluids based on their response to shear stress. Newtonian fluids such as water, oil, and air exhibit a linear relationship between shear stress and shear rate, resulting in constant viscosity regardless of the applied force. For instance, the viscosity of water remains unchanged whether steered slowly or rapidly. In contrast, non-Newtonian fluids deviate from this behavior, with viscosity varying depending on their shear rate or stress. Examples include shear thinning fluids like paint, which flow easily under stress, and shear thickening fluid like cornstarch slurry, which resists rapid deformation. This distinction is critical for understanding flow behavior in complex systems, as non-Newtonian fluids often require specialized rheological models for analysis. Basic concepts of viscosity and flow behavior. Viscosity is a measure of fluid resistance to flow, defined as the ratio of shear stress to shear rate. For Newtonian fluids, viscosity is a constant property, but for non-Newtonian fluids, it is dynamic, influenced by factors such as shear rate, time, and stress history. Flow behavior in non-Newtonian fluids is characterized by phenomena such as shear thinning, decreased viscosity with increased shear, shear thickening, increased viscosity with increased shear, and viscoelasticity, combined viscous and elastic response. For example, ketchup exhibits shear thinning, flowing more readily when shaken, while silly pudding displays viscoelasticity, stretching slowly but breaking under rapid force. Understanding this behavior is essential for predicting fluid performance in processes like mixing, pumping, or coating. Rheology, the science of flow and deformation. Rheology is the study of the flow and deformation of materials, particularly fluids and soft solids. Under applied forces, it provides the framework for analyzing non-Newtonian fluids by quantifying their response to shear, compression, or extension. Rheological properties such as viscosity, yield stress, and elastic modulus are measured using instruments like viscometers and rheometers, which applied control shear or oscillatory forces. Rheology is crucial for developing mathematical models such as the power law model for shear thinning fluid or the Maxwell model for viscoelastic fluids to predict the flow behavior in real-world application. Applications of rheology span industries, including food processing, example texture of yogurt, pharmaceutical, example drug suspension, and polymer manufacturing, example extrusion process. By bridging physics, chemistry, and engineering, rheology enables precise control and optimization of non-Newtonian fluid systems. Classification of non-Newtonian fluids. Time-independent non-Newtonian fluids. Time-independent non-Newtonian fluids exhibit viscosity changes solely as a function of shear rate, with no influence from the duration of applied stress. These fluids are categorized based on their shear stress-shear rate relationship. Shear thinning pseudoplastic fluids. Shear thinning fluids decrease in viscosity as shear rate increases. Common examples include paint, ketchup, and polymer solutions. For instance, stearin paint reduces its viscosity, facilitating applications, but regains thickness when at rest, preventing dripping. This behavior is often modeled using the power law model, where the flow behavior index is less than 1. Shear thinning arises from the alignment of molecules or particles under shear, reducing resistance to flow. Shear thickening dilatant fluids. Shear thickening fluids increase in viscosity with increasing shear rate. A classic example is a cornstarch water mixture, which flow easily under low shear but become solid under rapid stress, such as impact. This behavior results from particle crowding or jamming under high shear, increasing resistance. Shear thickening fluids are less common but find applications in protective gear, such as impact-resistant vests. Bingham plastic fluids. Bingham plastic fluids require a minimum yield stress to initiate flow, behaving like solids below this threshold and flowing like Newtonian fluids once exceeded. Toothpaste and mayonnaise are typical examples. They remain stationary until sufficient force is applied. The Bingham model describes their behavior, incorporating a yield stress term. These fluids are critical in applications like drilling mods where controlled flow is essential. Time-dependent non-Newtonian fluid. Time-dependent non-Newtonian fluids exhibit viscosity changes based on the duration of applied shear, reflecting structural changes within the fluid. Thixotropic fluids. Thixotropic fluids decrease in viscosity over time under constant shear as their internal structure breaks down but recover viscosity when shear ceases. Paint and yogurt are thixotropic. For example, stirring yogurt makes it thinner, but it thickens when left undisturbed. This reversible behavior is due to the management of molecular or particle networks. Thixotropy is valuable in applications requiring controlled flow, such as printing inks. Rheopathic fluids. Rheopathic fluids less common increase in viscosity over time under constant shear with the structure rebuilding under agitation. An example is gypsum paste, which thickens during prolonged mixing. Rheopexy is rare but relevant in specific industrial processes such as ceramic slurry preparation. The time-dependent buildup of structure distinguishes rheopathic fluids from thixotropic ones. Viscoelastic fluids. Viscoelastic fluids exhibit both viscous and elastic properties, storing energy like solid and dissipating it like liquids. They deform under stress but partially recover their shape upon stress removal, as seen in polymer melt and biological fluid like blood. We have examples of viscoelastic fluid. Common viscoelastic fluid include polymer solution, dough, and biological fluids. For instance, blood viscoelasticity affects its flow in arteries, influencing cardiovascular modeling. In industry, viscoelastic fluids are critical in processes like polymer extrusion, and food processing, where elasticity impacts texture and flow. Their dual nature poses challenges in design and analysis, but enable unique application. Flow behavior of non-Newtonian fluids, shear stress and shear rate relationships. The flow behavior of non-Newtonian fluids is characterized by complex relationships between shear rate, force per unit area, and shear rate of deformation. Unlike Newtonian fluids, where shear stress is directly proportional to shear rate, non-Newtonian fluids exhibit non-linear relationships. For shear thinning fluid, shear stress increases less than proportionally with shear rate, reducing viscosity as shear increases, as seen in paint. Rheological models for non-Newtonian fluids. Rheological models mathematically describe the flow behavior of non-Newtonian fluids, enabling prediction and process design. These models are essential for simulating fluid dynamics in industrial and biological systems. Then we have the Bingham model. The Bingham model applies to fluid requiring a yield stress to initiate flow. Described. Okay, so I need marker. Okay, for the Bingham model, it says the Bingham model applies to fluids requiring a huge stress to initiate flow. Described. Here, this formula, where they say where U is plastic viscosity, for T and no flow of this. Two space, two space, two space and drilling mods are Bingham plastic, remaining static until sufficient force is applied. This model is critical for applications where controlled flow is needed. Then we have Maxwell and Kelvin Volt models, viscoelasticity. Viscoelasticity fluids are modeled using framework like the Maxwell model, serial combination of spring and dashpot for liquid like behavior, and the Kelvin Volt model. The Maxwell model, the Maxwell model defined by okay, this is the formula for the Maxwell and Kelvin Volt models. They say where G is the elastic modulus and N is viscosity, describes stress realization in polymer melt. The Kelvin voice models capture scripts in doughs and biological tissues. These models are essential for understanding phenomena like dye swell. Flow in different geometrics. The flow behavior of non the flow behavior of non-Newtonian fluid exhibits distinct velocity velocity profiles compared to Newtonian fluid. Shear thinning fluid show flatter velocity profile due to reduced viscosity near pipe wall, enhancing flow efficiency. Bingham plastic may form a plug flow region where a shear stress is below the yield stress, as seen in two-space extrusion. Viscoelastic fluids may cause pressure losses due to elastic effects. These behaviors are critical in pipeline transport of slurry or food products. Then we have complex geometrics. In complex geometries such as mixer or extruders, non-Newtonian fluids exhibit non-uniform flow field. Shear thinning fluid improve mixing efficiency, while viscoelastic fluid may cause flow instabilities like vortex formation. Computational fluid dynamics (CFD) is often used to model these flows, accounting for geometry-specific effects. Understanding flow in complex geometries is vital for polymer processing and biomedical application. Then we have applications of non-Newtonian fluids, industrial applications, food and beverage industries, cosmetics and personal care products, oil and gas industry, polymer processing, then we have under biomedical applications, we have blood flow and biological fluids, drug delivery systems. Then under emerging applications, we have smart fluids, printing and additive manufacturing, experimental and computational methods for non-Newtonian fluids, rheological measurements techniques. Accurate measurement of rheological properties is essential for characterizing non-Newtonian fluids, enabling the study of their flow behavior and development of predictive models. Challenges in modeling non-Newtonian flow. Modeling non-Newtonian flow presents several challenges due to the complexity of their rheological behavior. First, selecting an appropriate rheological model is critical. Oversimplified models like the power law may fail to capture yield stress or viscoelastic effects, leading to inaccurate predictions. Second, time-dependent behavior such as thixotropy or rheopexy require complex constitutive equations that are computationally intensive. Third, viscoelastic fluid introduce additional challenges as their elastic memory effects cause numerical instabilities in CFD simulation. Then we have non-Newtonian fluids in drilling operations. In the oil and gas industry, non-Newtonian fluids, particularly Bingham plastic and Herschel-Bulky fluids, are used as drilling mud to facilitate exploration and extraction. Drilling mud suspend cotton at rest due to huge stress and flow easily during pumping. Shear thinning behavior, optimizing drilling efficiency. Viscoelastic fluids in polymer extrusion. Polymer extrusion used in manufacturing plastic fibers and films relies on viscoelastic non-Newtonian fluid such as polymer melt, which exhibits both viscous and elastic properties. Challenges and future directions for non-Newtonian fluids. Limitation in current understanding. Despite significant advancements, the study of non-Newtonian fluids faces several limitations. The complexity of their rheological behavior, such as time-dependent effects, thesotropy or rheopexy, and viscoelasticity, makes it challenging to develop universal models that accurately predicts flow behavior that predicts flow across diverse conditions. Advances in rheological modeling. Recent advances in rheological modeling aim to address these limitations by developing more sophisticated constitutive equations and computational tools. Generalized models such as the Hertzsprung and the Old-Rod-B models better capture yield stress and viscoelastic fluid, improving predictions for fluid like drilling muds and polymer mills. In conclusion, in conclusion, non-Newtonian fluids are indispensable in modern technology, driving innovation across industries. In food and cosmetics, their rheological properties ensure product quality and process efficiency, as seen in shear thinning sources and thesotrophic creams. In the oil and gas sector, Bingham plastic drilling must optimize extraction under extreme conditions. Biomedical applications leverage to the viscoelasticity of fluid like blood and cardiovascular modeling and the shear thinning behavior of hydrogels for drug delivery. Emerging technologies such as emerging technologies, then the ability to tailor flow behavior through rheological design underpins advancement in sustainability, healthcare and manufacturing, making non-Newtonian fluid a cornerstone of technological process. Thank you, sir.
Thank you very much. Please, can we clap for him again? Thank you very much. At least you were able to do something on the board. Thank you very much for the presentation. All right, you said that is N. Is it N or me? Which one?
This one.
For viscosity, I think it should be mu. Something like that. All right, thank you.
That's like using